All right, good afternoon and welcome everyone. So it's my pleasure to introduce our Colloquium speaker for the day, Professor Joseph Ford. He directs the Photonic System and Integration Lab in the Department of ECE at University of California, San Diego. His lab focuses on doing work in free space optical system design, prototyping for applications that have free space communication, fiber optic switching, solar concentrators, lighting, and especially on compact high-performance imaging, which I think we'll see numerous examples of that today. Professor Ford holds a degree in physics from UCLA and University of British Columbia, and in optical engineering from Rochester Institute of Optics, and a PhD in applied physics from UCSD. During his tenure in industry, he worked at Bell Labs in the Advanced Photonics Research Department, where he demonstrated the first MEMS spectral equalizer and wavelength add drop switches, and he later became the chief scientist of the optical micromachines before joining UCSD in 2002. Professor Ford is a OSA fellow and is a co-author on over 200 journal articles and several US patents. So I think with that introduction, I'll hand it over to Professor Ford.
Thanks, Simon. So first of all, can you hear me? Is this mic working? Yeah? Okay. So I will be talking today about work that is collaborative, specifically including people from my group here at the Photonic Systems Integration Lab, people that have since, several people have moved on. And these are the main collaborators at Distant Focus, and there are other collaborators as well on this work. But I'm going to kind of select and dive into one particular kind of imaging system. So what the talk is going to cover, first of all, motivation for panoramic, high-resolution, high-performance imaging, a brief discussion of the DARPA SCENICC program, and then talking about the basic approach that we're taking on this, which is monocentric imaging onto a focal surface that's curved. I'll talk about that imaging, the lens design, first of all, and on using optical fiber bundles to couple that spherical image surface to a focal plane, one or more focal planes. And then I'm going to talk mostly about some prototype imaging systems that we've been working on over the past couple of years, including some work on image processing that is quite important in making a beautiful picture. Then I'll just give you some hints on what we're doing next. So first of all, motivation. People are very excited now about panoramic immersive virtual reality imaging. They want to take cameras into situations and record a panoramic image. So you can imagine, for example, when they do an action-adventure movie, in a Bourne movie, they had the guy jumping through a window, jumping off a roof. He flew through the air, crashed through a window, did a roll, tuck and roll, and on with the chase, right? What you may not have noticed at the time that happened was that the cameraman jumped behind him and flew through the window, and they actually recorded it that way. And that's pretty freaking impressive, actually, especially in terms of the cameraman. But the thing they want to do next is they want, instead of having a conventional, relatively single perspective camera for that kind of action adventure, they want you are there, right? Every direction, every way you're looking. And for various applications, you'd love to record these things in super high resolution for posterity. For example, Paul McCartney's last concert or something like that, right? And the problem is that although these have been very successful and quite a bit talked about, they really represent a compromise. And the compromise can be identified. These are small cameras with small pixels. A GoPro, although an excellent camera, a really outstanding camera, is a 1.55 micron pixel. It has a limited dynamic range and a limited electron well depth. It is intrinsically not a great sensor. It's relatively easy to make that lens, but the sensor limits your performance. So when these guys make their cinema, they're using a bigger pixel, like a 5 micron pixel, and a relatively gigantic camera with a very large lens by comparison, right? And why do they do this? Why do they sell these rather expensive cameras? Because the performance is really great. So the trick is, how do we get this system miniaturization, get this focal length lens into the volume of one of those lenses? By retaining the focal length, you retain the large pixel and you retain the large electron well depth and dynamic range. So you need to shrink the lens, and we want a wide angle lens that can be shrunken. The motivation for this project was, in fact, local hero Mark Neifeld, a professor at UAZ now, but a few years ago he went to DARPA to have a vacation of working 60 or 80-hour weeks or something. And he started this DARPA program, which I ended up performing on. The DARPA SCENICC program stands for Soldier-Centric Imaging with Computational Cameras, was intended to be a broadly scoped research program on computational imaging. It ended up a little bit dialed in to smaller, more focused technology development. But the original system that we were making was these goggles, super glasses for soldiers that basically have a wide-angle, high-resolution camera at both temples and a real-time image processing and display that allows the soldier to see better than he would otherwise. He's also able to record the scene or transfer it or superimpose information on him. So it's basically your everything box. It was a super hard technological goal. At the onset of the program, we involved a lot of people and a very broadly scoped research. But as we went along, the new program manager, after Mark felt the call of academia and came back to Arizona, the new program manager said, all that stuff's kind of weird and it might not work, but that's a cool camera, make it better. So what he said was, spend more money on the camera, spend more time on the camera, make it work really well. And so I got a chance to spend a lot of time on this camera, which is what I'll tell you about now. So a basic concept is an old idea, recently gaining some currency because Sony has been publishing first a patent and recently some papers at the VLSI Tech Symposium on curved image sensors. And basically they found a couple of things. They found that the sensor could actually perform better when slightly curved, and they also said that the lenses worked better if they got a little Petzval curvature. It simplified the design of the lens. Now the lens would be integrated directly with the sensor and be higher performance. And we say, great. So the obvious question is, if a little curvature of the image sensor helps lens performance, what happens if we really use a lot? So the answer is monocentric lenses. So here is a wide-angle retro-telephoto lens that uses aberration vignetting to maintain a uniform illumination across the field. And this is a database designed from ZBase. It's f2. We had to push the performance a little bit. We wanted light collection. The resolution is not bad. But when we try and shrink it, the resolution drops like a rock. And we had to push up the F number more. So what do you do with these curved image sensors? The answer is you construct a lens very like that ball of glass in the lobby that Jose Sacian made, a monocentric lens, a spherical optic, in this case composed of two concentric surfaces with an aperture stop. The radius of curvature is equal to the focal length, and the performance of this lens is just amazing. It really is just amazing. So we want to work with that. Now, we did some lens design. You can just throw this into Code 5 or Zemax and let it rip. Or you can, given the simplicity of the lens, you can actually make an analytic solution for concentric spherical surfaces. We were apparently obsessive and did a design where we took every single glass. What we found is that we were finding a lot of variation in performance with different glass choices. And what we ultimately did was we explored every glass combination for a 2-lens and later a 3 concentric shell surface. We ended up with a ranked combination list, 365,000 combinations, which you could basically just go down and say, can I buy this glass in this thickness? Is the thermal coefficient of expansion too different? And will somebody make it for me? And you can end up with a very good lens. And this is what it looks like. 2 concentric surfaces and a stop, spherical image surface. There is an optical element here. It's not really for the lens performance. It's for mechanical mounting of the lens. The lens is this 2 spherical surface. And if you design it at infinity, then you can think of this as being a radially spherical surface at infinity or a planar surface at infinity. It's the same thing. Detailed design is here. This is SLAW 79, SLAW 13. It's an achromat. And there's nothing too surprising here. A few silica for the mounting meniscus. It doesn't really matter what that material is made out of. And the really interesting thing that we found, first sort of surprising thing here, is when we went to focus it. We originally thought we were going to focus it by moving the lens in sort of 3 dimensions to focus the region of greatest interest. But we found ultimately that if you just do axial translation of the lens, as you would in a normal lens, you can just say to yourself, well, I've changed the image conjugates for sure. It probably should come to a focus someplace on some kind of surface. And the answer is, it comes to a focus. If you design it for a flat original conjugate, it comes to a focus on a flat local conjugate, which is a really surprising result. I would say. We checked it like 3 times until we believed it. That's actually why we did this rigorous analysis, because I was doubtful of that result. So just a couple of examples. Here's a retro-telephoto wide-angle lens, 50 millimeters focal length. Here's a cell phone, small aperture, wild A-sphere, focal plane cover lens. So these are standard lenses with planar focal surfaces. If you make them with monocentric optics and a spherical surface, what you find is that the small lens can be made not smaller but simpler, and the big lens can be made both smaller, simpler, and higher performance. And this for actually a wider field of view than that shows. So it's a great idea. And these aren't the only kinds of lenses you can make. You have lots of degrees of freedom you can mess around with. You just have to maintain a hemispherical symmetry, and you can do all kinds of stuff, which is actually a fairly broad design space, more than you might think. You can get lost in this. So what we did was we did global optimization, mathematical optimization for these as seeds for the design. Then we introduced lens splitting and changes of the number of degrees of freedom to introduce the ability to compensate specifically and primarily for spherochromatism, which is the primary residual aberration here. So by splitting this and following King's Lake, as is always a good idea, then we end up with a lens that can be higher performance at a longer focal length or over a larger spectral range. The way we did the design is we start with one of these guys as the seed, split an element, then do some hammer optimization for glass substitutions. And once we have a pretty nice candidate pool, it's actually a fairly messy optimization surface. We ended up with some kind of mathematical optimization that drove us into particular designs that work very nicely. It took a lot of computation, but if you're interested, there's a reference where we give lots of design examples. We made an infrared one, we made a big one, we made an underwater one. It's lots of fun. We didn't actually build these, but fun to design. So fun to design. Back to the 2-glass lens, and this is really a hoot. So I asked my student, Igor Stamanov, who was about to graduate, I said, what is the actual resolution that this 2-glass combination can get to? And it's a harder question to answer than you might think of, because you have to choose all these different dimensions: focal length, f number, sensor pitch. We took a design technique which would basically say, pick a structure, pick a aperture, f number, and then scale up the focal length, looking to see what resolution you get. Obviously, if you scale it up long enough, then the aberrations start hitting you, and you lose resolution. And then to say whether we have resolution or not, we picked what seemed to be techniques used in DSLR cameras. If you look at Canon's lenses and ask what contrast they're getting, you can pick some fairly arbitrary metric, which is 3 times Nyquist at the MTF50, and you can find that for a given f number, like let's say f1.7, then as you scale up the focal length, you can get more and more information until you get to a certain limit, and then it's just getting bigger. There's no actual information. But how much information is the really cool thing? 2.3 gigapixels in a camera the size of a golf ball, roughly, because you use a very high resolution sensor, 1.1 micron, that's basically standard, and you map this entire surface. It's actually 3 times the surface area of a DSLR full frame camera, and that's a pretty impressive performance in that swap. But the funnest thing is to go up here and ask yourself, at what f number do you get to the absolute max? At some point it's a pinhole and it stops getting much resolution. The absolute peak is an f5.6 camera that uses a 3.3 micron sensor, and it's somewhat large, right? It uses a large curved sensor, 13,000 times the area of a full frame sensor, and it produces 2.6, not gigapixels, terapixels. And I claim that I am the first person to talk about terapixel imaging. So there. So that is scaled, by the way, to me. So Igor had some shrimpy guy that was only 1.75 meters tall. But even so, that's a pretty heavy lift, and we're not planning to build that. But it's amazing, right? This is a really cool lens design space. The problem, of course, is this spherical sensor. But the lens itself is amazing. And you might think that we're going to take a bow and say how marvelous and genius we are. But no, that would be wildly inappropriate, because the first such camera was actually used to record photographs from the Civil War, 1859. Oh, genius. He didn't have a spherical sensor. he took cylindrical pieces of film. This is Thomas Sutton. And he stopped this sucker down to like f30. And at f30, it's not hugely high resolution, but it's very panoramic. It was a pretty good camera, and it was sold commercially. I've got some advertisements for it. A little bit more recently, at least a slightly more recent conflict, was a much more complex lens, higher resolution, especially since he actually went and fabricated this spherical film emulsion, film negative. And it was something done for World War II, and they tested it for surveillance. It worked fantastically, but it was just horrible to work with these emulsions, right? Creating them, developing them, and printing from them was a limitation. So when we talk about monocentric lenses, the real problem is the image sensor. Now, you do have an option. So this is something that we played around with. You can design a lens, a monocentric lens. This one has 70 millimeter focal length, and it produces a spherical image surface. And if you had a spherical sensor, you'd be golden. What you can do instead is relay that image from this surface to a focal plane here. You can actually correct for the field curvature. And what you see is that over some limited region here, some of the light goes all into that aperture. Some of it goes partially into that aperture. And very importantly, you can get quite good performance. This was a near diffraction limited for a 1.4 micron pixel sensor, 14 megapixels, a nice camera. And the cool thing is that once you built one lens, you build a second one, you put it right next to it, and the light that is on the intermediate regions, if you design it properly, divides into both apertures, and it goes over there. So you might think we're going to see power splitting 3 dB between the two cameras. You actually need 3 cameras because it's a two-dimensional surface. But if you introduce an aperture stop here in this camera, what you can see is that you can actually push this to very uniform resolution across an arbitrarily large field of view where there is no aperture stop in the monocentric ball. It's just carried in these relay optics. Relative illumination is great, and the overall resolution is actually quite large, 2.2 gigapixels. This is a really cool lens design, a nearly perfect lens design. And you may think, well, no one would ever build that. But fortunately, DARPA has more money than sense and funded David Brady to work on this very large multi-scale imaging. My contribution was to bring in the monocentric stuff and do the design, sort of generalize the design. His contribution was building a gigantic and complicated system. So here's the CAD renderings of 221 micro cameras. If you look at this, you might say, well, that's a complicated system, but not really. The complicated system is the mechanics and the electronics for acquiring all that data and processing it. This is an early form of the camera. That's the 70 millimeter focal length lens and some computers for acquiring just a couple of fields of view. And then later they fleshed it out. This is about 75 of the image sensors, and later they put even more. So it totally works. But I'll just say, although an amazing camera, capable of gigapixel video, it has a very limited user base because relatively few people have the money to pay for the system, and perhaps more importantly, nobody has the memory to store the video that it generates. It just spews data at such a massive rate that no one can really make much use of it. What you use this camera for is actually kind of a viewport where different people are looking out in different directions, or you do real-time image processing. This is all cool, but realistically speaking, too complicated. So we want to simplify, and we simplify with imaging fiber bundles. So an imaging fiber bundle, I brought some here. You guys should come and check this stuff out. So imaging fiber bundle here is a high index contrast, dense fiber array with thin cladding and large cores, and it just basically transfers an intensity distribution on this surface to that surface. And if you polish the surface spherically and you make that surface planar, then you can stick it on there and transfer the image. Now, I didn't invent fiber bundles either. Schott makes them for various applications, including all kinds of night vision and fiber faceplates for CRTs originally, and they're high performance and they work well. All we have to do is stick the focal plane on the back, and we have something that can capture at least some fraction of the total field of view. If you like, you can put a bunch of them on there, and now, unlike the relay imaging, all the energy that hits that point goes boom down to the sensor. If you happen to hit exactly on the seam, you might go through if there's a gap, or you might split between the two. But in general terms, it's capable of collecting a lot of information. So again, take a bow, super genius, invented fiber-coupled monocentric lens imaging. I actually thought that I'd invented that for a while. It was a gleeful time. We had originally did this for an eye model, and I was just like, wow, we're smart. We did some publications and got a little bit of press. And then a very angry email from a guy who basically contacted not me, but the dean of engineering, saying that I was a fraud and a thief and a cheat and not acknowledging his work. And it was kind of fair in a way, because he had done exactly this system. Monocentric, two-glass, fiber-coupled focal plane, and it worked, and it was flown in space, used as a star tracker, and even done a big one, which was multiple fiber bundles, in this case intensified CCDs, also used for some defense and space applications. The reason in my defense I didn't know about it is because they didn't publish the camera. I think it was classified while they were working on the camera. It smells very much like Strategic Defense Initiative work to me. What happened was, at some later date, after the camera guys had all been laid off, the cameras remained and were used for a couple of applications. So it actually got published in very peripheral ways in the literature, but the only real document is a Lawrence Livermore internal organ magazine article. It's where I got these color pictures. And after I explained to the guy that his work was insanely cool and that I was jealous of him doing it, and we will cite him left, right, and center, then we're all friends again. And we go on. So I didn't necessarily extol in any detail that I thought this work was kind of missing the entire point, though. Because why are you making a monocentric lens? You could make a focal plane, and over a 60-degree field of view or a 50-degree field of view, you can get very good performance. This really is overkill and kind of painful. What you want to do is extract the value, which is resolution and field of view. So finally, at this point, what is new in this presentation is this kind of work where now we are concentrating on extracting both high resolution and wide field of view out of this system. So on with the show and imager prototypes. This is the Lawrence Livermore system. The engineer I spoke with said he was kind of surprised on how poor the light coupling was over the field of view. It got dark at the edges, and it only captured about a 50-degree field of view. This was slightly surprising, given that the fibers were an Na1 fiber capable of transferring light at any angle. If you mess around with these fiber bundles, you'll see that light incident at a very grazing incidence comes out the other end. So why wouldn't it couple? The answer is because you haven't got a flat surface here. You've polished it radially. Light, the chief ray, is injected perpendicular to that surface. And if you think about how waveguides work, then you're really not getting that refraction that makes you guide. And at some point, of course, you're going to go right through the sidewall. And it turns out that that's what limits this. You can model it. It's actually a harder problem than you might think, because you really have to look at skew rays and diffraction and all kinds of stuff. But you can get a pretty good model using Fred non-sequential analysis. This is a simple singlet lens, f4.4. And you model this, and you find that the coupling efficiency, I think this is just for the chief ray, but it looks very similar when you look at the whole ray bundle. You see it dropping by 3 dB for a 60-degree field of view, and it drops pretty fast thereafter. More importantly, and kind of interesting, the light that leaves the fiber starts leaving at really large angles, because the light remembers the launch, and it leaves with that same angle. So if you have the sensor in contact with this surface, great for you. That's pretty hard to accomplish. Generally, there's going to be some glue, and in that glue, the beam is going to spread. So that's important. This is something you can test, and if you guys are interested in messing around, you can come up and play with the fiber bundles and see this happening in real life. So this is basically the constraint on field of view of a single fiber bundle. Now, what about resolution? Fiber bundles are amazing. Schott has spent so much time on this. We came to them, and they basically said, we've got a fiber bundle that can be 2.5 microns pitch. Isn't that amazing? And I said, what about 2, 1, 1.5? How short can we make it? And they're like, well, we really don't spend any time on that because no one ever wants it. I definitely want it. So we paid them to draw a single bundle to lots of different lengths and cut and tested it at all the different lengths, because that's basically the pitch reduction. It's all the same structure. It's just getting smaller and smaller and smaller. And what you find is that the 2.5 micron bundle works great. This image is extremely saturated, actually. If you saw it in a linear domain, you wouldn't see anything that looks like crosstalk. And in fact, what may look like spreading is actually the light adjacent on 2 fiber cores. At 2 microns, you're starting to see a little real crosstalk. At 1.5 microns, it's got significant crosstalk. Below that, it's kind of a disaster. So that's with the standard fiber structure, and we want to improve that. So the question that we had, and given it was a DARPA program, we got to play with it a little bit, was how can we redesign the fiber bundle to make it work at higher resolutions? And what can we do? So this turns out to be much, much harder than you might think, because in order to model it properly, you have to have fine structure and then very long propagation. And you have to carry all the modes because all the modes transfer its Na1 fiber. So it's kind of a nasty calculation, and I'm not the principal guy involved in this. I was working with Vitaly Lomakin at UCSD, and I had a student working on this. Eventually, I went, and he went to work with Vitaly, and we tried something which is modeling this with rigorous coupled wave analysis, the obvious thing you would do. And what we found was pretty irritating. The theoretically predicted performance was terrible compared to the experimentally measured performance, which is not what you usually get, right? Kind of disconcerting. And we spent a lot of time on this, and we looked at different modeling techniques, and we made it more and more accurate. And the more accurate we made it, the more definitely it said your fibers don't work. It's like a bumblebee, right? Cannot fly. Until I can credit, this is actually something that people have encountered in waveguides and telecommunications and planar light wave circuits. But until you do something which is kind of blindingly obvious in retrospect, you make the fibers not exactly the same. By introducing a small change in the fiber core size, you frustrate the coupling of the fundamental and higher modes. And basically what happens is the light just doesn't want to jump. It can't easily transfer to the adjacent fiber. It kind of looks like it has to jump to the second adjacent fiber. Just as a general rule of thumb, it looks like you've doubled the cladding thickness. And the interesting thing is you don't have to introduce much variation at all. For a 2-fiber unit cell, you introduce 2% variation, and suddenly the performance is great, right? And then we did 3-fiber unit cells. It's kind of the same thing. It turns out to be very robust to the particular structure you take. Now, this is for a sort of 2-dimensional fiber. We want to model something that's more similar to the 5-sided fiber bundle that Schott makes. So that's something like this. The unit cell is this, and there's a little absorber at the center of this. It has the same index as the cladding. This turns out to be a product of refinement, trial, and error over 20, 30 years of improvement. When we looked at a regular array, we found that the mode launched into the center starts coupling into the adjacent fibers. But when we introduce 1% disorder, and if you look at this, you can see that there's a slight disorder, it actually stays much better confined. And so that's what it takes. If you want to be more accurate about what they actually fabricate, you can actually get an SEM. You can edge trace this, and then you find that at 2.5 microns, it's got great confinement. But at 1.5 microns, not so great confinement. So now finally experiment and model are matching. And it allows us to do what we wanted to do in the first place, was basically modify the fiber to improve spatial resolution. What we had to do, we tried various things, was increase the cladding thickness, decrease the core. And what that means is we can achieve confinement at a 1.5 micron pitch, but we must sacrifice transmission, 50% instead of 70%. And you might say, oh, I'll gladly do that. But remember, the fiber glue gap really is acting as the gatekeeper to spatial resolution. So making the fiber infinitely fine doesn't guarantee you an infinitely high resolution image. Plus, the lens may not be that good. So what you have to do is build it. If you build it, you will know. Here's the fiber, photographs of it, lots of cool dislocations and scratches. Here's the sensor, 1.75 micron pitch. And now the fiber bundle polished, spherical on one side, flat on the back. It's actually got flat sidewalls for reasons that will be obvious in a minute. You can cut it in half with a diamond saw and zoom in again with an SEM. You get these great high contrast images because the index of refraction is so different between core and cladding. And you can measure the glue line thickness very accurately, and it might amaze you that by this manually assembled part, we're getting a very uniform 0.9 micron glue line thickness between the fiber bundle and the surface of the sensor, which is, in fact, the lenslet and the Bayer filter underneath. So now the total thickness between here could be reduced by stripping all this stuff and using a black and white sensor. You may not want to do that because you have to bear in mind that there's a differential thermal expansion between these two materials. And if you try and push this too hard, they will separate. They can separate. But that kind of tells you that we don't necessarily want to go to a finer pitch fiber after all. This is a good one for us, and we should be able to make it work. Now, the lens that we built, this is actually it, if you're interested in coming and looking at it. This is a 12 millimeter focal length lens, 120 degree field of view. Fairly expensive, but entirely conventional. Designed for the visible light spectrum, and it produces 45% measured contrast on axis at 200 lines per millimeter and 30% at 300 lines per millimeter. That's really good. And a more complicated lens, this is actually the more complicated lens, including that internal air gap for spherochromatism, let us spread the response out to the full CMOS sensitive band. So this is a camera lens intended for a monochrome, night vision-y sort of starlight imager. And the resolution was maintained despite the increased spectral band. It was very good. Testing these kinds of lenses is a pain because we don't have a spherical sensor. So what we do is we look at it with relay imaging. We don't have to worry about getting these close together. We're just testing the lens. And you can measure the MTF across the field of view at some distance, which is 1 meter in this particular case, and then reduce it to half a meter and refocus, and we see that it's retaining MTF pretty much with the tolerance design. So it's behaving very nicely and focuses properly, and everything is actually pretty good for green for go. So now go. Put the lens, in this case, just the bare lens, and we look at it with the microscope. Looking down through the lens, we see a region of the field of view, and we can zoom in and see what we're getting with the lens. This is actually an f1.35 optic. There's a little halo, but really good resolution at 170 lines per millimeter MTF 50. Now put the fiber bundle on and look at the back of the fiber bundle with the relay optics. You have to be careful about light collection because sometimes the light goes out of the microscope. But if you zoom in enough, you see the fiber cores and you see what happens to the sampled image. There's also some loss. This isn't a good indication of loss because light doesn't necessarily go into the fiber, into the aperture of the microscope. But the interesting thing to do, of course, is to put that fiber-coupled sensor on here, detect the image digitally, and zoom in again. And now we see the result of all that fiber coupling, transport, emission is reflected in a drop of the MTF 50 to 70 lines per millimeter, significantly worse than the original MTF. And you might say, too bad. But remember that we're trying to compare this to other existing imagers. So we picked this lens. We love this lens. It's a zoom lens from Canon, retro-telephoto, conventional full-frame sensor, designed for a 5 or 6 micron, well, 6.5 micron pitch focal plane. We kind of pushed it by putting our 1.75 micron focal plane at the back of this. We focus at the center, move over to the side, and we look at the resolution as a function of field of view. And we compare it to the monocentric lens with the fiber coupling. We only have one fiber bundle here. In principle, we can put more, but we can look at any point on this lens and we can see the same image is captured, and it looks like it's working pretty good. But it's actually working better than pretty good because this lens has significant aberration, lateral color. There's distortion, which you can correct digitally, but there is a loss of resolution compared to the fiber lens. And now, here's the surprise. This has very poor aperture efficiency. If you look at the exposure, this camera actually has both higher resolution and a shorter exposure for the image acquired. It's a quarter the exposure, despite that this is the aperture instead of that. And that's just the way that retro-telephoto lenses work. So it's working pretty good. If you zoom in enough, you're going to see a couple of things happening. These are the effects of fiber coupling. These are not dead fibers, but fused fibers. When the fibers fuse, more light gets into the cladding, it tends to attenuate, about 50%. But in general terms, this is a much higher resolution than that, despite the size. So this is an exciting sort of first indicator. But we got to go further. First of all, in general terms, we're dealing with a really interesting system where light is going through a linear space variant imaging transfer. It's linear space invariant over a small region. Then it goes through this discontinuous sampling, some really interesting and, i.e., very hard to predict coupling. The waveguide transport, this is a Fred simulation which shows these cool spiral modes. They exist. The light actually is doing that. It emits, and finally you sample it. So if you're Mark Neifeld or maybe Ahmed Ashok, then you will say, ha-ha, nothing here is anything but deterministic. I will reverse that entire process. I will get the information that entered this system, and I will take the detected signal here, and I will calculate what started there. Absolutely, it can be done. We can't do it yet, but it's an interesting problem. What we will do is the very first level of image processing. So this is the fiber sampling. You see a little bit of a moire pattern here and defects. The interesting thing is that the same moire and defects are there for a white field. So the first thing you do is something very equivalent to sensor calibration. You take this image and do a point-by-point dot divide here before you de-interpolate, demosaic, and you get this significantly improved image. So it's just a sensor calibration, and you might say, well, that works, but things can move. That might not work, might not be robust. What if the sensor's too small? Well, we did it with a 1 micron pitch sensor and a 2.5 micron pitch fiber. This is really going to guarantee horrific moire because of the RGB color. Now, the pitch of the RGB pixel, superpixel, is almost identical to the fiber. It's the worst case, and it looks horrible. The moire is nightmarish. And when you compensate it, it looks pretty good. So it actually works. So good. Second question now is, how robust is this? It works for a range of sensors. How robust is it, for example, with temperature? The glass and the fiber and the silicon in the sensor expand differently. So fortunately, we were allowed to mess around with that. We had some funding from Google on this. So you start with the red channel, and you see this horrific moire. Do some local Fourier transforms to quantify it, and you end up with a heat map. Red is bad, and moire patterns are bad here. Why is it better at the edges here? I won't go into it, but it basically amounts to loss of signal. But basically, this is bad. Then you compensate it, and it mostly goes away, and you get a nice, clean image. So this is sort of an indication that you get uniform image. But the amazing thing is that this is 20 degrees different temperature. It's calibrated by the wrong temperature, and so it's stable over a 40-degree temperature range. So it's actually pretty robust. So we are now cool on fiber-coupled imaging and ready to go with our prototypes. First thing we do is we build the multi-bundle sensor that will allow us, unlike this one, to capture a wide field of view. With a high-resolution fiber bundle with a high-resolution sensor, we're getting a lot more information. And this is what the prototype looks like. The lens in a more or less conventional mount with axial focus is attached to fiber-coupled sensors. We put them as close as possible, and we get a slice of this image. We call this a letterbox. It's like a 10-to-1 aspect ratio image, but it's a very wide field of view, 124 degrees field of view, actually. And put it together in a pretty straightforward way. These are the two cameras side by side. To test this thing, we had to put a really big res chart up in the lab, and from the camera in the middle of the table, we're imaging from wall to wall. And there's very fine features on this res chart that we're looking at with our camera and with our benchmark cameras. So just to give you now quantitative information, this is our benchmark for resolution. It is the DSLR full-size camera. And this is our benchmark for size, and the goal is that resolution with a lens that size. Take it outside and go to town. So the Canon lens, I want to be very clear, is a 21 megapixel, very large field of view lens. We're cropping this to the letterbox that we're actually acquiring, right? So we're throwing away most of the information. We're actually keeping, I think, about 2 megapixels of the image. But that's okay. We're only imaging one slice. Put the GoPro, we do the same thing to it. We get a good image. They're both great images. Now we put our camera here, and what you see is discontinuous regions. This seam is pretty good. This seam is terrible. They're all pretty bad, actually. But the cool thing is the resolution, because when we zoom in with our benchmark imagers, we're seeing not great resolution. When we zoom in with ours, much better resolution. And there's no cheats here. This is very high resolution over a very wide field of view. Now, the seams are bad, and you've lost information. Those actually came from some machining errors in making the bundles. So we went back and we did it again. This time, we made machining of the bundles ourselves, actually. Got a much tighter fit on these, rebuilt the sensors, rebuilt the camera. We've used 5 instead of 6 sensors because we swapped out the lens to the wide 4-glass wide spectrum lens. And now, when you assemble the imager, this is with no interpolation. This is just the images put side by side. We undistorted them and put them side by side. You can't really see the seams anymore until you zoom in. You can see where the seam is because this one was vertically offset from his neighbor. So here's a seam. If you zoom in, you'll see it's about 8 pixels of this fine pixel sense. And of course, you can interpolate across this. So it's a pretty good image, and we're going to town. We're doing well. We want a full field of view imager. The only problem is we have to assemble a 2-dimensional array of fiber bundles. This is hard. The way that we set out to do it was to do it in slices. So basically what happens is you create sensors, you put them on a flex, you create the bundles in a slice, in a fixture. You can even polish off the glue in between. You qualify the slice. When the slice is good, then you populate as many slices as you want to get the full resolution camera, which looks like that. And it's an amazing camera. And I didn't even talk about the focal plane, which is a full custom focal plane. It's not quite ready for publication, but it's actually coming out of fabrication finally. And we should be talking about it in about a month and a half. That's Forza Silicon's focal plane, which is foveated, low power dissipation. This camera is up to 85 megapixels per frame and up to 100 frames per second in a camera, the physical swap of a GoPro approximately. It's really cool, but this is the camera we were told not to make because it was just heinously expensive. A lot of the expense is in the assembly of very expensive focal planes. The focal planes, I won't say how much the focal planes cost, but I will say they're really expensive. And then the yield wasn't 100%, and assembling this thing was going to make, we were going to make one. The original goal of SCENICC was to make one camera and say, woohoo, look at it. But the program manager after Mark said essentially, why can't you make something that could be commercialized? Could this be commercialized? We admitted that it couldn't. What we wanted to do instead was use monocentric lens with a single full-frame image sensor. Well, that's a challenge for fiber coupling. One thing you can do, and this is extremely cool, is bend the light before it gets to the fiber and make it couple in. So you can use straight fiber bundles if you can use a conformal surface beam deflector. And one way to do that is with microprisms, which are relatively easy to make. They aren't perfect. In addition to coupling the light we want, they always have the return facet if they can be embossed. Anyway, in fact, no matter how you make them, there's always light that goes the wrong way. But we built this thing as a side project, lots of fun, and we showed that it could work. What you see, this region is where we embossed a little strip of microprisms. It's visible there. And there you can see the light is actually getting through. And when you look at a wide field of view image, we're extending the field of view by a factor of 2, which is cool. But I don't have a zoom up of this because it didn't improve the resolution. The resolution was not great. And in fact, the way to make this thing is a much more physics-oriented thing. Shia Feynman, working independently on the SCENICC program, has been exploring conformal nano antennas, which basically are, you can think of them as an infinite index metal layer, essentially planar. You can think of it as a perfect prism. It will bend whatever angle you want, and it has 0 thickness, right? Or you can think of it as a plasmonic antenna. And he's done some experimental work that basically shows that it can work, but it's only in design. So the question is, how are we going to actually build this thing in the short term? And the answer is, we're going to do something completely different. We're going to curve the fiber bundles so that they point at the light that's coming in. And if you do that, the light will transfer. You actually excite higher order modes in the fiber. It does blur a little bit, but you can get uniform coupling across a wide field of view. It can work very well. The trick is, of course, making this three-dimensional fiber structure with high index contrast, super high resolution fibers. You would think that this was science fiction. But no, SCHOTT to the rescue. SCHOTT provided us with exactly the structure we needed, which they had done for a completely different application, which was demagnifying fiber bundles. So if you guys want to come up and check this out, this is a SCHOTT fiber bundle, more or less standard product. It takes this size image and it demagnifies it to this size by the fiber taper, or you run it backwards and it magnifies. They use this for all kinds of applications. We identified that inside that bundle are the paths that we actually want. So if you map them out and you just define a surface for the intercept of the spherical image and the planar image, then you can put the lens on one side and a full frame sensor on the other, and you get a pretty good approximation to an ideal three-dimensional fiber bundle. So now there's some design work here. I'm going to just sort of sketch it. It's actually pretty tricky deciding what taper is optimal and where to put the bundle exactly. You move this in from the planar end. You move that in from the waist. Just to give you a sense, the fibers really follow something very close to a sinusoid. We've measured it by cutting them in half. You can define the angle of intercept and try to minimize that. And then you can look at, if we had a straight bundle, it drops like a rock, and no coupling here. With a tapered bundle, depending on the ratio, you actually get that angle of intercept to basically stay closer to perpendicular. And In fact, if you use the right taper ratio, it kind of goes up and gets slightly better midway through. We wanted a 126 degree field of view and a 23 by 23 millimeter focal plane. So the end of the design process, we end up with the fiber surface angle coupling that looks like this. It drops from 90 to 80 degrees, well within spec, and much better than the straight fibers would have been. The core pitch changes from this point to that point. That proves to be a problem because when the core expands, even though all the light is coupled from here to there, it gets dimmer. You're spreading it over more area. So we're going to see some vignetting across the field, not from loss, but from expansion of the image. But it should work. All you have to do is build it. Now, this slide is an instantaneous overview of the process of making a curved fiber bundle. Distant Focus came up to this job. We couldn't find anyone to do it for us, so we did it ourselves using something that's very similar to your more. You have a 350 FG. This is its predecessor. It was actually formed by a DARPA program. DARPA paid for this. It's Center for Optics Manufacturing in Rochester. They built this massively over-engineered thing called the Moore 500 FG. 500. More than 350. It's not as good as the 350. It doesn't have the degree of freedom to make super freeform surfaces, but we don't need freeforms. And it's micro-grinding, and it allows us to directly control exactly the shape we want. It's quite critical. The shape has to be quite precise. This is a real bear to make, but Distant Focus is doing really wonderful work on making the fiber bundles. And there it is. Okay, so there's the fiber bundle. Zoom in under the surface. You can kind of see that it's bending the light and collecting from the entire back surface and bringing it out the face. This already has a meniscus lens sort of stuck to the front, which helps us to basically, there's two reasons for that. One is that you don't really like to have an exposed focal surface for dust. And secondly, if the surface is not perfectly specular, and this allows us to index match it and get nicer coupling. We can test it now and put a laser beam and measure the transmission efficiency as a function of angle. And we can measure the beam divergence as a function of angle. And this is done in air, but in fact we're going to glue it to the sensor so you can compensate for that transmission into the 1.54 index adhesive. And we see that it's actually doing pretty close to our design value. The 70% efficiency is for coupling into the index matching gel 1.5. And it retains that efficiency over 128 degrees field of view, just exactly as designed. And then it drops like a rock. So it worked. The divergence is similarly within spec, 20 degrees inside the glue, and this should work. So we're ready to go and test it. Take the monocentric lens and put the fiber bundle behind it, and again, with the microscope, look at the back of the thing to see what we're seeing. And we're seeing the full field of view image as before. If you look on axis with just the lens, you see a nice resolution spot. With the fiber, actually, if you happen to land on the fiber core, it doesn't blur at all. If you land at the intersection of 2 or 4 fibers, it blurs into those fibers, but it works very well. At 60 or 50 degrees, plus and minus, I think this was primarily driven by the fact that the light is coming out at a cone angle and we couldn't collect it. We're getting some blurring, pretty much according to what we expected from the lens, and it's working nicely. And we're ready to go. Put this together onto a really expensive full-frame sensor. The best sensor that we could get access to is a 4.5 micron pixel pitch, 25 megapixel sensor. You put a little glue in the center and you drop the bundle on. It's a little more complicated than that, but not a whole lot more. Cure it in place, attach the meniscus lens, and Bob's your uncle. So this is our sensor. One thing we were very concerned with here was CTE mismatch between the glass and the silicon. So what we did was we built one and we cut it in half. Because, well, actually before we cut it in half, we temperature cycled it. And it survived. Hooray. Then we cut it in half, which was not really very nice, but allowed us to look at the glue thickness. And what we found was that we were getting very close to the glue thickness that we designed to. We actually deliberately introduced a little more glue thickness. We calculated how much it needed to stretch and provided it enough thickness to stretch. And these are 3.8 micron pitch fibers, which the sensor pitch is 4.5 microns. So we're going to get a little blurring, but it should be within spec. And now the imager itself. So this is actually the final form of the lens. This is actually being assembled now as we speak. The only real difference is that Whereas before we have a two-glass lens and it's focusing back and forth. In our current imager, it's exposed to the world and the thumbs of people around. In the final sensor, which is supposed to be a little more robust, we put a dome, protective dome in front of it. But it's basically the camera. And we use a little stepper motor for focus, a really beautiful sort of optomechanics designed with distant focus's help. It's very dense as an imager and very small as a camera. And that's what it looks like. Where here is our monocentric lens, stepper motor, the sensor, FPGA, and communications boards, which are stacked up. Same sensor without the fiber or the lens. We can attach a lens to a conventional lens and compare them directly. So that's our camera and our benchmark, or one of two benchmarks that we could use. The software interface, also provided by Distant Focus, is a real-time video relay. You can't really display it in real time. It's too much information, but you can dump it into memory and do some basic image processing. And you can look at things like impulse response, which are not perfect, but they're pretty much at the design value everywhere except in the corner where it's badly blurred. So what's going on? The answer is the focal plane's not flat. The focal planes are bowed because people don't usually care that much. We really care. So you could compensate by polishing the back of the fiber bundle to match it. We don't have the time, or maybe we don't want to polish an aspheric surface on the back there, but it can be done, and we can retain good resolution of the whole field of view, but pretty good. And again, the trick is to compare it to the benchmark imager. So first of all, that vignetting leads to a flat field image that's bright in the middle and dim at the edges. You can do the same calibration technique and get a relatively good image, but you're sacrificing dynamic range. So what we did to make that better is we introduced an attenuation in the center field of view with a Gaussian apodization filter that made this much more uniform and gave us better dynamic range. So we're actually doing this. And the second thing we're doing is we're putting a color filter in front of the camera, which will ultimately be fabricated as that dome. But that's the camera. And now the test. Here's our Canon DSLR, this guy. Here's our GoPro, not seen in this picture. The Canon lens directly on the sensor, that's this guy. And the curved fiber bundle imager, that's this guy. He has the apodization filter and the color filter, but you can see the camera underneath there. The fan is to cool this thing because it's capable of acquiring some massive number of pixels per second. It's a video camera, not a still imager. And if you zoom in, then what you find is that we have a smaller pitch sensor and we have a longer focal length lens, so we get higher resolution. The Canon lens directly onto the Vita sensor is slightly better, but the fiber-coupled image is nearly equal. So it's achieving its goal of miniaturization without compromise in resolution. Now I'm going to talk a little bit about truth and beauty. So Amit, if you had gone to ICCP, this was the picture we showed at ICCP, the first letterbox imager acquired. And we were pretty proud of this image because this is the high-resolution image. It's also horrifically ugly. And when you compare it to the DSLR, what you find is this has all kinds of resolution. But this is the picture you'll show to your friends. We had to make them prettier. You saw the image that we made better in this one before. But the point is that in order to sort of demonstrate our camera's capability, we had to work on image processing. We had to master all the tricks that people generally use. So here it is, the image processing chain. Here's the raw image before we do the calibration. Calibrated, it becomes more uniform. It's still grayscale. We demosaic it using an edge-aware demosaicing. It's a Malvar algorithm. And the colors look like crap. We were stuck here for a while. Eventually, we twigged that you do color compensation using a color chart. You basically do a matrix multiplication on each point. And suddenly now you've got dynamic range and color, and it's pretty. And you then can take it into something like Photoshop and make aesthetic choices. How bright do I want it to be? Light and shadows, things like that. Now when you adjust saturation and color, now when you do white balance, it looks good. Whereas if you don't do this in particular, that image never looks great. So the big question is, how does it work compared to our big camera, our benchmark? And the answer is, it looks pretty good, actually. Curved fiber bundle image is less distortion, uniform across the field of view. The pixel resolution is not perfect, but it's very good. and it's very small. So this is an interesting camera. Now, this is the big picture. You have to blow it up to see how the resolution is maintained. And what you find when you blow it up enough is that there is some noise here. And I don't know entirely how much of this noise is due to the fiber coupling and how much is just due to the sensor. But in any case, we can apply a standard denoising technique called BM3D, which smooths it out at a cost in resolution. Then we can sharpen it back up again with unsharp mask. And now this is our apples to apples comparison with the full skies imager. This guy is our tiny camera. This is our large camera, and they're looking very good. So if you're quantitative, we can look at MTFs and edge scans. What happens is before we do all that sharpening, it's a little bit less resolution. After we've done all the sharpening, it's a little bit higher resolution. But the bottom line, it looks pretty good. So now I'm going to show you. Oh, this is going to be interesting. Go away. All right. I'll show you a video. This is a video camera, 25 megapixels per frame. That frame I showed you was a still frame from a video image, and it's working quite nicely as a video camera. There's all the things you want, and you can imagine using this as a video camera. But realistically speaking, that's not a good use of this camera, because this camera has very high resolution, and it allows you to do something more like this. You have an object, you have things happening, and from your full field of view, you can zoom in and still have a very high resolution image. Or if you zoom in enough, maybe you're interested in the clown who's juggling, and you have an image which doesn't look that great, but just for comparison, this is our benchmark camera. Now, this is an unfair comparison because the Canon can't record at full bandwidth. It is, after all, just this little consumer product camera. It down selects to a 1080p image at 30 frames a second. And if you do the same zooming on the Canon, then what you see is it's got significantly less resolution if you zoom in enough to see the clown. Then, let's see if we can get him on the screen at the same time. Then you can see the resolution is much better. Now, I want to make it clear, if you had a Red Epic camera, you would see this resolution for sure. But still, it's a comparison of the performance of the two imagers. So I'll go back to this now. And I didn't show the video of the GoPro, which is kind of impressive in a way. The GoPro actually has pretty good resolution. I love that GoPro camera. But it's got a very low dynamic range in the acquired image. They've basically compensated for that small pixel, which saturates very easily, by the way. If you look at GoPro video, they're constantly saturating. And to extend the dynamic range, they compress the thing. So that allows them to see into shadows and brights reasonably well, but it is a loss of resolution. And the goal here basically is to get that kind of large pixel performance in that kind of small camera format. So final future directions, well, what we're doing this summer for fun and profit, and I emphasize that it's still summer in San Diego, because this deliverable is supposed to be done this summer. We're going to take, instead of this single aperture camera, we put 5 of the apertures into a very compact format. This is a cool system. It uses fiber optics. Tom, you'll like this. Ribbon fiber transceivers to send data at full bandwidth. And there's like 5 ribbon cables to 5 computers, which basically suck the image in at full resolution. And the goal is to make a kind of super high resolution, very compact camera. This is with the optional, DARPA didn't fund it, compact interface, but that's what our cinematography camera might be someday. That said, for cinematography, one thing you'll discover if you talk to the cinematographers is they don't like a fixed aperture. So monocentric lenses, which are made of solid glass, have a fixed aperture. That is not good. They will not accept that. So we've designed this lens. It's in fabrication now. It actually uses an oil as the central element. and it uses a variable aperture in that oil. It's sealed in the oil, and so this focuses, and you can adjust the aperture using sort of stepper motor control, and this will be the cinematography version of our camera. It's actually being funded by another military application, but it's looking very good. And then in a more researchy vein, NSF is combining with Intel and funding us to work on a form of light field imaging. Now, light field imagers work very well, but are typically not good for wide field of view, which has to do with the lens design more than anything else. A monocentric light field imager potentially could do some really amazing things. One of the things you can do is pull the aperture out of the central ball and retain, complete uniform field illumination across the field of view. So what we're doing with this contract is building a letterbox imager with micro lenses embossed onto the fiber-coupled sensors and messing around with the image processing to take better advantage of all those pixels that it can offer. So conclusions. This is a diagram of sort of standard photographic lens families. If you add to this diagram the monocentric lenses, we've got the aware relay imager, and then the SCENICC designs and the virtual stop, like that light field imager and some other techniques that we're using for that. It could be quite a new domain for wide field imagers. We have built one. It does work. We're doing the final integration for the photonic mast, and there's still a lot of interesting stuff to explore. So with that, I will conclude. And ask for questions. And by the way, I've got lots of toys here if you guys want to look at stuff. You can see, for example, the sensors and the lenses.
Questions? Yes, Ray.
What's that? Oh, yeah. Well, I'm not as good as some people in the company. We have a video of Chris LaRue juggling 5 clubs, for which I will always hate him. Not only can he juggle 5 clubs, he'll juggle them up, spin around, and then catch them and keep going. It's just like her.
To rub it in.
Yeah, just to rub it in.